All right, good afternoon, everyone. Thanks for attending today's training. We will be discussing, sorry, Robbie, we will be discussing the mechanical ventilation strategies for residential. Sorry, I still have the refrigerants one up there. But these trainings are sponsored by the Colorado Energy Office with training materials created by Build Tank. My name is Erica DeLello. I'm a project manager for Noresco. And if there are any issues with audio today, please feel free to write me in the chat. So just to give you a little background on some of the work that Robbie and I have been doing, we've got a whole bunch of different types of trainings that are offered throughout the state. We've got, of course, this Wednesday webinar series with a couple of changes for the next couple of sessions. Since the 2024 IACC has not been released yet, we are going to be changing the next two topics to the following. So next week's will be lesson learned from the Marshall Fire from a codes perspective. And then on the 26th, we'll be covering commercial air barriers. We will reschedule those IACC 2024 versus 2021 trainings to probably next month, but we're just waiting on that 2024 IACC release. So we do also have role-based trainings, and these are a great resource for folks that want a comprehensive overview of the code from their specific perspective. So if you're an architect trying to comply with the code, we're going to walk you through all of the energy code requirements and then how it actually pans out on a real plan set and a real project example. And we'll have different activities throughout the training sessions so that the folks that we are training are fully engaged and being able to apply the code requirements in real time. And then we also, of course, do virtual and in-person trainings for just requested topics. And then all of our webinar series are available on the Code Adoption Toolkit. The recordings are posted there within a week or two, so give it a little time. And then for these trainings, continuing education credits are usually sent out at the end of each month. So we just actually sent out the ones from May yesterday. So if you didn't receive yours, please let me know. But you should have those now. We do also provide technical assistance for code adoption throughout the state. So if you're a jurisdiction that's looking to update to the 2021s or even considering the 2024s and you want to talk about it, we're here to help get your jurisdiction up to code. And so we can support you guys in a bunch of different ways, whether or not that's stakeholder engagement or city council or writing the codes or reviewing your code amendments, all of that kind of stuff. We're here to help. And then lastly, it's that Code Adoption Toolkit. It's a great resource to everyone. We are updating it as soon as 2024 IACC's released. We'll have new resources for that as well. But the tool that I want to highlight today is the Colorado Codes Helpline. And this is a helpline where anyone can submit a question on any of the iCodes as it relates to codes in Colorado. So you submit a question and we'll get back to you within just a couple of days' time. And yeah, so with that, I'm going to go ahead and pass it over to Robbie to start his presentation. And just a friendly reminder that those next couple sessions topics did change for those of you who just joined. There will be an email that goes out shortly, probably tomorrow, with that information as well.
Great. Well, thank you so much, Erica. Appreciate it. We're going to dive in here. I'm Robbie Schwartz with Build Tank Inc., and we'll be talking about strategies for residential ventilation and indoor air quality. I'm going to actually turn my video off so you can concentrate on the slides, and I'll come back on the video when we finish here. Here we go. Okay, so we'll be talking about air movement, why we want to ventilate our homes, a little bit about local and spot ventilation. Most of what we'll be talking about is whole house controlled mechanical ventilation and filtration. There will be some poll questions that come up, but we don't have time to actually run a full poll because that takes some time. So be active on your chat and answer the questions on your chat there as we go. And we're going to start out with a poll question. And that first question is, can a house be too tight? And I'll give you just a few seconds to type in the chat here, get it, some dialogue going there, and would be interested to know what you think. Okay, someone, once I get the first one in the chat, I'll move to the next. Is there anybody out there? There we go. All right. Okay, so we got a lot of yeses there. And so that's one of the main reasons why I asked that question, because the real answer is no. Houses can't be too tight. We're actually asking the wrong question there. We need to gain control and predictability of the airflow. And in order to do that, we have to build our houses tight. And in fact, we want to build our houses as tight as we possibly can. So what is the real question? Well, it's the basis of this training today. Can our houses be underventilated? And that is a resounding yes. So what we are really looking at is kind of this marriage of building tight and ventilating right. And so one of these building science mantras that we have is build tight and ventilate right. And that's what we want to do. And we'll get into why we want to do that here in a bit. So building tight and ventilating right, you should not, we're gaining, what does that actually mean, I guess? Answer, type into your chat, I guess, which one of these things are a result ultimately of building tight and ventilating right. Anybody have a thought there?
I've got a raised hand, Robbie, from
Sure.
Mona. Mona, go ahead and unmute yourself.
Sorry, I hit that by mistake, guys.
All good.
Okay, so we see a lot of different answers there, but yes, control and predictability is what we're really after there. We've changed the way that we've built pretty dramatically from 1936 and in the past there, but we have these expectations of comfort, of efficiency, of safety, health and indoor air quality, durability. And in order to meet these core expectations, we've not only changed the way that we build these houses, but we need to build our houses tight and ventilate them right in order to actually achieve these expectations there. So when we're talking about doing that, we're talking about air and how air moves. And we can think about air as a freight train. It's a transport mechanism. Air is moving pollutants and heat and moisture around our houses and through our assemblies, kind of in the same way that this train is transporting coal, its cargo, from point A to point B. Now, the problem with the cargo that air carries is that it can deposit its cargo inside of a wall assembly, for example, moisture and heat and pollutants, but it has a very difficult time picking that cargo back up and taking it all the way to the outside. So it might travel from inside the house carrying some moisture and then get into the wall assembly and deposit that moisture into the wall assembly, but it can't pick up that moisture again and carry it to the outside through a hole very well. So that deposit, when it deposits its cargo, we often have a problem. When we're talking about air in our houses, we're talking about air in a cubic foot perspective. So a cubic foot of air is about the size of 4 basketballs. And we have this defined volume of air inside of our house. And that volume of air is constant. So if a cubic foot of air goes into the house, a cubic foot of air goes out. So you can think of about a basketball in and a basketball out. That's ultimately what's happening in our houses there. So we have the ability to control that in really one way there, because we have to have a pressure across the boundary here in order for air to move in or out. But we also need a hole in order for it to move in and out. And if we can control, we can have better luck controlling the holes in the building envelope than we do in the pressures, because pressures are created by wind or by what we call stack effect. When air warms, it rises and create pressures on the house. And even mechanical systems can create pressures on the house. So we're gaining that control and predictability of the airflow in our houses by closing up the holes and building a house that's tighter. And we're doing that largely from the perspective of better indoor air quality and background moisture control in our houses. So in order to ensure that we're getting those two things, again, we're building tight, but we always need to remember to ventilate right. So we learned even more than I guess we knew in the past that since the COVID happened there, that we spend a lot of our time inside and indoors. The EPA claims that pollutants are often 2 to 5 times higher indoors than outdoors. So even though the air outdoors can be polluted, especially here on the Front Range of Colorado, in the Denver metro area, sometimes we have those red pollution days. It's relatively cleaner than outdoors. And we often, depending on the ventilation system that we choose, we can filter that air and condition it in different ways as well. But you do have to be conscious, especially when maybe there's a fire or something else going on and we have that smoke-filled air, if you're going to bring that air in or out. And that's why we're going to be talking a little bit about controls and needing to control that ventilation air and have the ability to turn it on and turn it off there. But even if we do turn it on and turn it off, we always have to remember to turn it back on, because it needs to be running in our modern day houses there. There's this Dr. Corsi, who had done some research that kind of determined that our average lifespan is around 79 years. And we spend about 69 of those years indoors. Inside our homes, sleeping, inside vehicles, and only roughly 6 years of our 79 years are spent outdoors. So again, because we spend so much time indoors, we need to ventilate and condition that air and make sure that it's healthy and comfortable. Why it matters that air and the quality of that air that we're breathing has impacts on our bodies physically and mentally. It impacts the way that we breathe. It can impact the way that we think. So we want to ensure that we have homes that meet our modern expectations. So we apply the building science of gaining control and predictability of airflow, moisture flow, and heat flow. We ensure that the occupants have fresh air through filtration. And we've learned that now that we can add MERV 13 filters, that we can even filter out bacteria and viruses from the air. And so we want to make sure that we exchange the proper amount of air from the outdoors to the indoors through that concept of building tight and ventilating right here. So whole house controlled mechanical ventilation was one of the things that the residential energy field study that happened in Colorado right during the COVID time there, we realized and we found out that almost 50% of the homes in Colorado are not getting whole house controlled mechanical ventilation, even though it's been a requirement in the code since the 2012 IECC, and a requirement even before then if you're using one of the performance options in the code and maybe trading off house tightness for less R value. If you did that, you also had to install some kind of whole house control mechanical ventilation. So ventilation has been in the codes for quite some time, but we haven't consistently installed those systems in our houses. And that's one reason why I think we're seeing some issues or some complaints about our modern day houses there. Now, spot ventilation it's not as easily to define where it's required, especially in like laundries, for example, kitchens, bathrooms. Those areas are defined with spot ventilation requirements, and we'll talk about those in a little bit here in a second. But so we've talked a little bit about the air quality. Let's talk about moisture control as well. So obviously we don't want to have mold in our houses, but mold is a very common thing here. Mold grows wherever we have kind of paper-based products, and you see that all those paper-based products are those things that we like to build out of there. But we also have things like upholstery and other things where mold can grow. Mold ultimately needs a spore, it needs some type of nutrient or food, it needs a moisture and a temperature range that is ideal. And it's basically that range where we like to live as well there. So again, to gain control and predictability, we're not really going to be able to control the spore. We're not really going to be able to control the food or nutrients and or the temperature range. The thing that we can gain control and predictability of is the moisture level inside of our homes there. So that's what we're ultimately trying to do. So again, when we're talking about control and predictability, most often we're talking about gaining control of moisture, thermal energy, air, and potentially the drying and wetting mechanisms that are in our houses there. From a health perspective, however, it's a little bit different there than what our buildings want. So our occupants want a relative humidity somewhere in that 40 to 60 range, and we really kind of honed that in during COVID when we were emphasizing, I guess, ventilation a lot more than we were in the past there. But we need to ventilate our houses, but we also need to have a certain level of humidity for optimum health. Now, that humidity level isn't exactly what our buildings desire. Our buildings want drier is better there. We want to ensure that that moisture isn't destroying our buildings, and that whenever we introduce moisture to our buildings, we have the ability for that assembly to dry. So we always want to ensure that our drying mechanisms are greater than our wetting mechanisms when it comes to a house there. But again, moisture in our houses, especially from a relative humidity perspective, moisture that's in our air, helps us improve our health. We have fewer allergies, improved healing, improved hydration, and so forth and so on. So when we start talking about infiltration, which is air moving into our houses, versus ventilation, we need to step back a minute, because a lot of folks have this question that we're trying to build this really sound, airtight building thermal envelope, and then the question is, you're asking us to put a hole in that envelope and to ensure that we have proper ventilation. And kind of there's a dichotomy there that a lot of people don't understand. So we want to understand the difference between infiltration and ventilation. So infiltration and exfiltration just explain what happens with air leakage. Infiltration is air coming into the house. Exfiltration is air going out of the house, but it is unpredictable. It is air that's just flowing in and out through random holes in our building envelope. Now, these holes and the air that's moving through it are incorporated in our HVAC load calculations. We can measure that air using a blower door, but we want to strive to get more control and predictability of the air that's moving through these holes. So we're trying to tighten up that building thermal envelope there. But the big thing with regard to air leakage, whether it's air coming in or air going out, is that it's random and it's unpredictable there. When we're talking about mechanical ventilation, we are talking about control and predictability. So we have air that's coming in or out of the house at a specific rate, meaning that I know the cubic feet per minute of air that's moving through the holes in my building, whether it's a designed hole or a non-designed hole. We're also setting that fan that's moving that air in and out at a specific schedule. So I know the air changes per day, the air changes per hour. I know the cubic feet per minute that are moving through our houses. And that ventilation air, that air that's coming in and out of our houses, is also accounted for in our HVAC design there. Now, we have different types of ventilation systems, and some of those ventilation systems can help us gain even more control and predictability, because I might know where the air is coming exactly from, where the source of that air is coming from, what hole is it coming into the house through, and potentially what hole is it going out of the house from. We also can potentially filter and distribute that air in the ventilation. Now, the code doesn't require that we do this. Therefore, we need to understand when we're doing it and what type of ventilation system we're using, so that we can gain even more control and predictability. And we'll get to that when we talk about specific ventilation strategies here. But again, the primary function of mechanical ventilation is to provide the occupants with fresher air or more clean air, and also to have that background moisture control so that we're not getting condensation on our windows and we're not over humidifying a house that's ultimately going to create molds or mildews or other type of decay in or on our building assemblies there. So the mechanical ventilation is part of the energy code. It's also part of the IRC here. It's saying buildings complying with this section R402, which is the main requirement section for our energy code to build our houses tight and insulate them well, means that we also need to provide mechanical ventilation in our houses. It also goes a little bit further and says that we need to have intakes and exhausts, and they shall have automatic gravity dampers that close when the ventilation system isn't actually operating there. So that's partially has to do with whole house controlled mechanical ventilation, but it also is dealing with spot ventilation systems as well. So we're going to start with spot ventilation systems here, talking about kitchens, bathrooms, and laundries. You see here some locations where spot ventilation is talked about in the IRC. Rooms containing bathrooms, showers, spas shall be mechanically ventilated. And when we talk about kitchens, we are given a specific ventilation rate. So you can judge that either intermittently or continuous there. But we see that there's a minimum ventilation rate. Again, minimum isn't a bad word. It doesn't mean that we're not ventilating enough. It's just saying that if you're not putting in these mega kitchen hoods that push 1200 CFM of air, you have to have at least 100 CFM of air moving out of the kitchen when you're actually cooking. So that would be the intermittent, or you could run it continuously in that kitchen as well. And in bathrooms, we actually have a ventilation rate as well, documented in the IRC, that says we have to have a bath fan that moves at exactly 50 CFM of air intermittently. Now you can see the pictures below here, and why we now in the 2021 IECC have to measure these ventilation systems to actually see if they're pushing here, because ventilation is dependent on the fan, but not only the fan, but how the duct of that fan is routed from the fan housing to the outdoors. And we'll get into that a little bit more. With regards to kitchen ventilation, though, we know that cooking with gas releases a number of pollutants that we want to get up and out of the house as soon as they're produced there. And this is one reason why we are also talking a lot about electrification, especially electrification of cooking, because gas itself creates these pollutants that are harmful to our health. But we also see that electric cooking and any type of cooking can create ultrafine particles, and just the chemistry of the food changing will create particles and things that we want to get up and out of the house that are dangerous to our health there as well. So induction cooktops also need to be ventilated to the outside so that we're getting those chemicals in the changing food up and out of the house as soon as they're produced there. Exhaust hoods, why there's an issue with them. Ultimately, we see sometimes that the range hood isn't vented to the outdoors. So that is a requirement of the code, that it's always supposed to be vented to the outdoors. Sometimes the hood is so loud that it's not used. The hood maybe is ducted in a way that it's actually not moving air. The presence of recirculating hoods is an issue, but we'll see here in a second that there is a loophole there. Which I guess might take us to our next poll question. Can a recirculating hood actually be used? Can you install a recirculating cooking hood in a house? What do you think? So we got some no's, but mainly yeses. And the reality is that we shouldn't be allowed to, according to the code here, because the code says in the IRC that everything needs to discharge to the outdoors. And it talks specifically about ducts serving domestic cooking areas here. But there is an exception here, is if it's installed according to manufactured instructions. So it's a little bit of a loophole from my perspective, because it's obvious that if you have a recirculating hood, the manufactured instructions aren't going to include putting a duct system on it that's going to route it to the outside. From my perspective, we shouldn't be installing recirculating hoods, because they don't remove those pollutants, and it's a health and safety issue that we should get those pollutants up and out of the house. But again, there is this kind of loophole here. So really, everybody was correct if you answered no or yes to that poll question there. Now, again, outdoor discharge, we say that the air removed by every mechanical exhaust system shall be discharged to the outdoors and shall not exhaust into attics or soffits or ridge vents or any other places there. The only kind of rules that govern where those exhaust openings happen is this, what often is referred to as the 310 rule, to ensure that you're not putting an exhaust discharge too close to a window or door or any type of opening that would bring that exhausted air back into the home there. So you want to make sure that we're taking those pollutants out of the house, but we're not giving it the ability to come back into the house as well there. Now, dryer vents also should be exhausted to the outdoors. And all of these vents, we should remember, are supposed to be air sealed and taped or caulked or masticed, just like we seal other ductwork for our HVAC systems. These systems should be sealed as well. You can see the picture in the lower left-hand corner here. Whoops, I don't have in one of my slide presentations, I ended up putting little circles around here, but you can see that when we attach ductwork to the fan housing and that damper is located in the fan housing, sometimes the mechanical fastening screws can impede the movement of this damper itself. And that is one of the reasons why sometimes these fans are so loud, is that we're increasing the static pressure or the resistance to the flow of the air so much that it's creating so much noise. And that noise tends to mean that people don't utilize these fans. So whenever you hear noise, you want to go back to the installation, because our modern day fans, generally speaking, our modern day fans are very, very quiet. And the quieter they are, the more often they're going to be used, because people hate to hear the noise of the fan there itself. So again, obviously we don't want to vent into attics or other places there because we're going to end up getting mold or other things on our underside of our roof deck sheathing here in these areas, because often our ventilation of our roof and attic spaces aren't adequate to actually address the humidity that we might be pumping into that zone from a bath fan or something like that. Okay, so whole house controlled mechanical ventilation systems here. In the IRC and the IECC, it's triggered a little bit differently here. In the 2018 IRC, it was linked specifically to house tightness. But in the 2021 IECC, it's just a requirement. Regardless of how airtight the house is, you have to provide mechanical ventilation. And that makes sense because it was triggered in the 2018 based off of 5 air changes per hour. And there's nowhere in the United States climate zones where you can build leakier than 5 air changes unless it's been amended to allow that. So in essence, whole house controlled mechanical ventilation is a requirement. And again, as I said before, it's been a requirement for quite some time there. So mechanical ventilation systems here, the top above the line here is dealing with the IECC here, and it's talking about mechanical ventilation and it needs to be provided. And then in the IRC, in the M1505 section, it talks about the ability to use different types of whole house control mechanical ventilation systems. We can have a supply side, an exhaust side, or a balanced ventilation system. We have to have some type of controls that allow manual override, but we need to design them to run continuously there and design a specific flow rate for them. You are allowed to run them intermittently, but if you do run them intermittently, you have to increase the flow rate. So if I designed it to run continuously at 100 CFM, and I'm going to run it only 12 hours a day instead of 24 hours a day, I need to double the flow rate there to 200 CFM of air. So we want to make sure that we have these controls, that we have the proper ventilation strategies that we can choose from, and that we have the ability to run it at the specific rate or CFM there. Now, one thing I want to point out about controls is that we want to be able to enable manual override, but we don't want to encourage manual override, because these systems, especially in our modern day houses that are tighter, we want that ventilation system to run and run as much as possible, really continuously there. If they don't run continuously, you're going to see condensation on windows. You're going to see stagnant air that people can smell, different issues that come up. So we want to help educate our consumers and our contractors why we want whole house control mechanical ventilation in the first place, and why we want it to run continuously in the second place there. Okay, so we have these different ventilation standards that we can choose from, or strategies, I guess I should say, that we can choose from. Positive air pressure strategies, which would be a supply side, negative air pressure strategies, which would be an exhaust side, and equal pressure strategies, which would be our balanced ventilation strategies. But before we get there, let's think about the ventilation rate. The ventilation rate comes from ASHRAE 62.2. Now, ASHRAE 62.2 is referenced in the reference section of the standards there, but it's not called out specifically in the M1505 section of the code here. What they do is they give you this table and say, if you have 4 or 5 bedrooms in a house, and the house is between 1,500 square feet and 3,000 square feet, you need to provide 75 CFM of air continuously in that house for whole house controlled mechanical ventilation. Or you're allowed to use this formula. And this formula and this table come from the ASHRAE 62.2. I think that more people are utilizing the formula than the table that are designing the systems. And this is kind of the rationale why. If you see that for this particular house, the formula kind of right sizes the ventilation system in that house. Whereas maybe we're over ventilating if we use the chart there. Again, I think it makes sense to use the formula rather than the chart, but either of them are allowed from a code perspective there. The other thing that we know about whole house controlled mechanical ventilation is that we need to take our climate zone into account. There are some strategies that just don't make sense to use in specific climate zones here. So let's go through those ventilation strategies, starting with supply side ventilation. So supply only ventilation systems push air into the house. That brings air into the house, and it changes the pressure dynamic in the house. We always measure pressure across the building thermal envelope, because the building thermal envelope is defined as that boundary condition between conditioned space and unconditioned space, and pressures have to be measured across a boundary. So we see if we're pushing air into the house, we create a positive pressure inside the house, and that positive pressure might push air through our building envelope, through holes from the inside to the outside here. And that's why we need to think about the climate condition where we have that air. So this is a pressurization strategy. So it's, I'm trying to think, I think I might be wrong there when I say it's a moist climate recommended strategy, because you're, well, I guess so, but there are kind of two issues here. And why I'm stumbling here is because we have moisture inside our houses and we have moisture outside of our houses. And the reality is that if I'm based in Houston, for example, and I'm pushing moist air into my home, that could be a problem. The biggest problem, though, is the air that's inside the house that I'm maybe pushing through my building assembly. And if that air is moist as well, it could create a building durability problem with that house. So again, we need to think about the moisture zone that we're building in, whether it's a climate zone 1, 2, or 3, and if it's in climate zone A or B, the dry or the moist side of the equation there. Now, we don't have to worry about is backdrafting atmospherically appliances there because we're positively pressurizing the house. We do have possible building durability issues, but regardless of pushing air in and not knowing exactly where the air is leaving the house, we have gained control and predictability because we know, again, that air in equals air out. If I push a cubic foot of air in, a cubic foot of air has to pop out somewhere. I don't always know where it's going out of the house, but I can measure the fan and determine that it's coming in and it's coming out at a specific rate. So I know the runtime and I know the CFM that of air that's moving in. So I've gained more control and predictability. It might not be the best strategy for my climate or to get that control and predictability, but it's very cost effective. And that's why a lot of builders use it. Here's an example of a supply side ventilation strategy where we have a duct run from the outside to the return side of the furnace. So whenever the furnace is running, or I choose to control it to run, because I might add a controller like this air cycling device here that causes the furnace fan to run. This is on the return side, so it sees a negative pressure. I'm pulling air from the outside to the return side of the furnace, and I'm distributing it around the house there. So I'm creating a positive pressure inside the house. And I can use inline fans or this type of return side system to bring that air in the house and positively pressurize the house. So on the left here, I've got a duct from the outside to the return side of the furnace here, creating that positive pressure. On the right side, I've got the inline fan that is doing the same thing here as well. Now, you'll see on the left-hand side picture here, I'm not bringing in the best quality air because you can see that duct is ducted to the roof. And if that roof is an asphalt shingled roof, then I've got the pollutants from the asphalt shingles that are off-gassing, and I'm bringing those pollutants back into the house. That could be a problem there. Okay, and time for another poll question. Does the IECC require mechanical ventilation to be tested? Yes or no? Great. We see a lot of yeses here, and I have to say that it does, but only now in the 2021 IECC. So if you're not on the 2021 IECC, you're not required to test the whole house mechanical ventilation systems or the spot ventilation systems. But now in the 2021 IECC, we are required to test bath fans, kitchen hoods, and whole house control mechanical ventilation in accordance with the manufacturer instructions and is supposed to be conducted by an approved third party agency there as well, and they're supposed to provide a report. And there is an exception only with regards to kitchen range hoods. This exception comes directly from the Energy Star program that has been requiring ventilation testing for quite some time and has demonstrated that a significant number of fans in our houses are not pushing the required amount of air there. So we need to ensure that we know what code we're using and when we need to test, but it's not a bad idea to test even if you're not on the 2021 IECC. It, however, brings up a conundrum, especially with supply side ventilation systems. How do we actually test? And we need to design our systems to be able to test. And that's why I show this iris damper here, because if I put this iris damper in that duct that's coming from the outside to the return side of the furnace, then I can hook up what's called a manometer or pressure gauge to that black tap here on the damper here, and I can measure the flow across the damper, and I can convert that flow into, or that pressure into a flow number. And then I can actually dial in the size of this so I can get the right amount of air through the duct to the furnace there. Because just putting a 6-inch duct to the outside, I have no idea how much air is actually coming through that. So we need to look a little bit at how these systems are designed and to ensure that there's a measuring device on that so that we can actually measure the flow there. Now, the next strategy we have is an exhaust ventilation strategy. Exhaust ventilation strategy can be a single point or a multi-point fan that is exhausting air out of the house. Now, that fan creates a negative pressure inside the house. So again, this is better in a dry climate because the air outside is more dry than the air inside. So in essence, the air coming through the building envelope is drier, and we're going to have less issues from a building durability perspective. We want to ensure that we have sealed combustion or power vented appliances in our houses so we don't have any combustion safety issues in our houses. And again, we're gaining more control and predictability, but not as much as we could if I knew exactly where the air was coming into the house. I know exactly where the air is going out. I can put a flow hood or a flow box on it, and I can measure the CFM going out, so I know exactly the CFM that's coming back in the house. And I can put that fan on a control, so I know if it's runtime, I know the CFM rate, so I've gained a level of control and predictability, but not the best level of control and predictability. Again, this is a very cost-effective strategy, and that's why we see here in Colorado a lot of builders utilizing that strategy, or HVAC contractors utilizing that strategy, because it's so cost-effective. It's just the replacement of a bath fan in a centralized location with a high-quality fan that you can set the runtime and potentially dial in the flow rate. Now, you can kind of double up on these systems, or you can utilize a supply side system with an exhaust side system, and you can get a quasi balanced ventilation system, because I know now where the air is leaving through the exhaust fan and where the air is coming back in with that supply duct that's going to the outside, to the return side of the furnace here. And you see some systems out there that are trying to leverage this type of approach. This is called an air cycler system. And what it's doing is it's utilizing a supply side ventilation strategy when you are heating and cooling the house and the furnace fan is running anyway. You're doubling up on ventilating the house as well, and potentially conditioning that air that's coming into the house. And when the furnace fan isn't running, you're using this cycling control to turn on exhaust ventilation in order to better get continuous ventilation in that house and meet the ASHRAE 62.2 standard. So these controls are smart. They need to be connected to the devices that are used there, and they can make our systems work and work well and get kind of double duty out of a normal forced air furnace in our houses there. We need to be able to measure the flow rate here. So here's an example of a flow hood that can measure the flow rate of the exhaust ventilation system there. So we saw that it was difficult potentially to measure the exhaust rate or the supply rate on a supply side ventilation system. I just wanted to show you that it's really easy to measure the ventilation rate of an exhaust side ventilation system here, there. And once we know the ventilation rate, we can set often these fans with a timer, with a timing device, and potentially a CFM knob here, in order to gain better and better control and predictability through that exhaust ventilation system there. We're lucky in Colorado that both exhaust and supply side ventilation strategies work and work well, but there is no doubt that balanced ventilation strategies are the best strategies for our homes. The problem with balanced ventilation strategies are they are the most expensive strategy. They, however, work in all climate zones. They work regardless of the combustion appliances that we have in there. We're gaining the most control and predictability because I know the air, where the air's coming in and where the air's going out. And it's a neutral pressure strategy, so it's really best for the house there. How they work ultimately is that air is exhausted from inside the house, and that air goes across a coil. And you can see on the right side here that there's a coil, and there's kind of dedicated air streams in two different directions. Those air streams don't physically touch each other. You think of a corrugated box and air going in one direction through those corrugations in that box. The air's not going to touch the airstream that's going the other direction, but that corrugated box is also a heat exchanger and potentially a moisture exchanger as well. So we have air in general that's going from the outside, air that's going from the inside to the outside, which is exhausted from the house, which is carrying pollutants, but it's also potentially carrying moisture and heat that the house might want. So you can take it across the coil here. And then we have air coming from the outside into the house that's also fresher air, and it's going across that coil, and there's some level of exchange that's happening there. When we're talking about a heat recovery ventilator, it's only able to pull that air into the home and simultaneously exchange that air from the stale air from the inside to the outside. But while it does that, it's able to recover a portion of the heat that's moved there. So heat recovery only gives you the ability to recover heat. It doesn't give you the ability to recover moisture. So fresh air in, stale air out, and at the same time, we're recovering a portion of the heat. Now, these systems are somewhere between 65 and 90% efficient, depending on the system that you have there. But one of the things I should mention is that regardless of the ventilation strategy, there is a energy penalty due to the electricity or the watt draw of the fans that are used in here. So when you're talking about generating an energy rating index score for the house, for example, it would take into account the watt draw of the energy that's used to move that air with whatever specific fan there. In this case, it would also take in the recovery efficiency of the specific heat recovery ventilator that you were using. Now, an energy recovery ventilator has the ability to work in the same way that a heat recovery ventilator does, but it has also the ability, depending on the season, to move moisture and heat in a specific direction. So you can see in the picture on the left here that we have air leaving the house on the top here in the wintertime season here. And remember that in the wintertime season in Colorado, we generally have more moisture inside our house than we have outside the house. So you can see in the picture in the upper left corner here that air is leaving the house and it's moisture laden, but the air inside the house is gaining that moisture. Some of that moisture is being transferred into the incoming airstream. And with an energy recovery ventilator, energy or heat is also being transferred to that incoming airstream. And then in the summertime, we might have more moisture outside the house than inside the house. And we're trying to keep that moisture out of the house there. So what we used to think was that heat recovery ventilators were only able to be used in cold climates, and energy recovery ventilators were only be able to used in moist, warm climates. What we're learning now is that, yes, heat recovery ventilators really should only be used in cold climates, but energy recovery ventilators can be used in any climate zone. And so we're starting to see more and more of them being used in cold climates, specifically for that wintertime condition where we want to keep that moisture in the moisture-laden zone, which would be inside of our houses. And kind of in the summer, actually as well, we might be humidifying our houses, or just because our houses are tight, we want to keep that moisture level inside the house in our dry climate zones here. And often our dry climate zones, well, in Colorado anyway, our dry climate zones are also cold. So an energy recovery ventilator can do both things for us. Again, we have to be able to measure the flow through the fan and set that fan on some type of control. So there are different ways that you can measure the flow through these systems. Some of these systems have pressure ports on them where I can measure a pressure across the coil there, and I can convert that pressure into a flow number. Otherwise, I'm going to have to either put in that iris damper into the duct or use some type of pressure probe that I would insert into the duct itself to be able to measure the pressure across the duct there and try to convert that into a flow. I could do that with a supply side strategy as well, but you are putting a hole in the duct there. So regardless of how we measure pressure, remember, we also have to have controls on these systems. And there are a variety of different controls that you can choose from. But the big thing is the picture in the lower right-hand corner where this control is actually labeled. So if you can use anything from a simple toggle switch to something behind the switch plate cover. But regardless of the control that you use, there is a requirement now that that control be labeled. And the biggest issue with labeling is that we're trying to begin an education campaign to ensure that people don't disable their systems. They can turn them off periodically, maybe when there's wildfire smoke in the air or we have a high pollution day. You might want to disable that system and not bring in those pollutants into your house. But we want to ensure that that system gets turned back on, because ultimately these systems should be run continuously there for the occupants, remember, fresh air, and also for background moisture control there. And then we need to locate that intake, especially if we're using a supply side ventilation system or a balanced ventilation system. We want to make sure that these ports that where we're bringing air into the house are located so that we're not going to bring in pollutants into that house. So that example where the supply side strategy was taking air off of the roof, that's not an ideal location. Unfortunately, the code doesn't address this issue, but it definitely is, from a health and safety perspective, something that we should be looking at. And this goes beyond the 310 rule, where we're not bringing air that's too close to the exhaust back into the house. And that's kind of demonstrated here in this picture on the lower left-hand corner where the exhaust pipe is. But we also want to ensure that we're not taking air from animal runs or garages or other places where pollutants might be located there. And then potentially where snow might cover that exhaust as well, that could be a problem as well. Lastly, I wanted to talk about filtration. And again, it's not addressed by the building codes itself, but we need to think about filtration here. There are two ways to filter the air that's coming into the house. We can have a traditional forced air system, or potentially a whole house control mechanical ventilation system can ventilate air as well. Now, supply side strategies and balance strategies are where you're going to get that ventilation filtration. Exhaust side ventilation systems, there really isn't a meaningful way that you can ventilate that house there. I want to also point out the picture on the left here, because we see, especially in the past, we saw these filters installed in a filter slot, and that filter slot wasn't covered and gasketed. It's now a requirement that it's covered and gasketed, because it's included in the duct leakage of the system there. And that system, if it's not covered and gasketed, it's going to be very, very leaky, and it's on the negative side of the system. So we're going to be potentially backdrafting an atmospherically vented water heater that might be next to it, or any other kind of pollutant that might be near that filter slot is going to get into the system and be distributed around the house. Okay, another poll question here. What does MERV mean? Here's some examples of what it might mean. what does MERV mean and why? Well, we'll get into why we're using MERV rated filters, but does anybody know what MERV means or want to take a guess? Number 3, manual energy recovery ventilation. So MERV means minimum efficiency rating value. This is the system that is most often used to rate the efficiency of a filter itself. So the higher the number, the more efficient the filter is here. And you can see that a MERV 13 filter begins to be able to filter out bacteria and viruses as well. So since COVID, we're starting to see more and more MERV 13 and higher filters installed in our systems there. Now, the issue with that is that it's filtering out smaller and smaller particle sizes, which means that potentially they can get filtered, they can clog up more quickly and impact our HVAC systems if we're using them in those systems there, and that potentially the static pressure across the filter is higher, which is an important thing to know when we're designing these HVAC systems there. Because again, static pressure is the resistance to the flow of air across our system, which basically governs how much air can come out of a supply or go into a return boot in that HVAC system itself here. But what we've learned is that the higher the MERV filter we get in these systems, we have to get better quality filters installed. So this is showing the difference between a 1-inch surface filter versus a 4-inch pleated filter. And basically, we're increasing the surface area of that filter and reducing its static pressure and giving it its better ability to actually filter the air. These 4-inch pleated filters last longer. You don't have to replace them as often, and they do a significantly better job out there as well. But we have to, again, take this into account during the HVAC design, because the greater the pressure drop, the greater the resistance to airflow. And if we get that less airflow, we might impact the equipment and motor performance, but we also might freeze our coils or not be able to heat and cool all the rooms that we want to heat and cool. So this is just another chart that is demonstrating the benefit of going to a 4-inch pleated filter. You have to change it much less, but the 4-inch pleated filter ultimately works better and better than a 1-inch filter there. Now, you will see some other filter rating systems out there. The most popular one is MERV, which is the minimum efficiency reporting value there. But you see that 3M created their own system, and Home Depot even created a system as well. But I would always recommend that we stick with the MERV system because it's the most well-known system, and it's was created by ASHRAE, which is a great standard setting body there that is kind of not trying to market anything like 3M or Home Depot might be trying to market things. But we also should remember that filters can't cure all of our indoor air quality problems. They don't necessarily do anything with moisture, and depending on the filter that you choose, it might not be able to clean all of the indoor air pollutants that are moving through that filter there. So we want to pick the right filter for the right application there as well. So that brings us to the end here, where I just want to reiterate that we need to leverage that sound building science. The sound building science is wrapped into these codes, especially our modern day codes, where we want to build tight, we want to ventilate right in order to have healthy occupants and to have that background moisture control. And ultimately, we get what we inspect, not what we expect. So we want to ensure that we are inspecting these houses correctly so that we're getting systems installed that are required, but actually are functional and work for our houses there. So thanks so much for your time. Appreciate it. You can reach out to me anytime you like at my email or phone. And I am more than happy to stick around and have a discussion if anybody like to ask a question or make a comment.
Thanks, Robbie. As always, great presentation. So yeah, we'll go ahead and open it up to questions if you guys want to raise your hand or write in the Q&A or the chat. We're here to help, but I'm going to go ahead and stop the recording, and yeah, Robbie and I will stay on for more minutes.